Alright, provide the IUPAC name for the following. Alright, I have a substituent off of my ester, but this is one of these trickier esters where the carbonyl is directly connected to a ring. So we're going to have the substituent cyclohexol space. Then we're going to list that cyclopropane. How about pentane? And then we're going to do carboxylate. Cyclohexyl, cyclopentane carboxylate. Alright, question 13. Starting ethynyl chloride. Synthesize ethanamide. Alright. That's mostly straightforward because it says neutral reagent. Don't really have much choice on that. We follow how our book introduces it. You could do an NH2 negative, but NH3 is typically more what we'd expect anyway. That's like what we did up here on the examples, and we always had to do 2 of them. So I'm only going to draw the 1. It doesn't want us to do the mechanism, but that is going to react, replace that bottom. We're going to need 2 NH3s altogether because the other one is going to take that extra hydrogen and that chlorine and make an NH4 plus Cl. So it end up neutralizing the extra chlorine that was floating around in there. That's why we had to have 2 of those. Alright, now, not going to do, I could do the mechanism to show that all out to you, but I kind of don't need to because I have that exact same type question right here. I have a amide and I have an acid chloride. So I'm going to show that mechanism on this one. And it's technically this mechanism right here. Because even though that's an OH rather than an NH, it's still going to do the exact same thing. I'm just going to do something slightly different with that base. Alright, so my very first step, I'm going to put the nitrogen's lone pair right there. So I can draw its attack to the back side of that carbonyl. And scroll down a little. So right below this, I'm going to draw that resulting compound, which is going to have an O as a negative, a chlorine, and then an NH2CH3 and positive. And I need to do another arrow there where it shows that electron go up. Alright, still have both these hydrogens. That's why this thing's still positive. So I need to do another attack of this to get rid of that hydrogen. I don't like where I put that arrow. I want to show that arrow going at one of those hydrogens. Now, on the example given, it was just a base. But since we have this floating around in here anyway, I'm going to show it's what does the attack. And more specifically, I want that to be the nitrogen that does the attack. Alright, so this is going to turn into still a negatively charged species because that O negative will stay there. Chlorine is still on there, but this is now an NHCH3. And floating around in here somewhere is a protonated amine. Alright, now this next step goes just to stabilize that charge. We move that down, kick off this chlorine, and that gives us this guy, and that chlorine ends up attached to that NH3 that we just made. You could draw it with positives and negatives, or you can lose both those. But 3 steps, 3 steps. Same as given there in our textbook. But that could be any neutral nucleophile. Any negatively charged nucleophile will go in the 2-step pattern instead, because it doesn't need to actually kick off or deprotonate whatever we put on there.